we'd like to look at some applications of using a Taylor series to do certain types of estimations. Now let's suppose we want to evaluate the following integral. You notice that sine x squared we don't have an antiderivative for, plus we want to evaluate it at limits of integration. So if we can't integrate it, then how do we attack it? Well, the simplest way is to use the Taylor series. Since we know that the Taylor series for sine x is as follows, if I replace the argument here with anything, I will simply replace the x with that same thing. So right now, if sine of x squared is the same power series, but with x squared in here, and then we get this quantity right here. Now the integral here, if we replace the function with the power series, we have the integral of an infinite sum, which seems kind of daunting, but we know from Calculus 1 that the integral of a sum is always the sum of the integrals. So we can literally swap places the integral symbol in the summation. So what we have is the sum of an infinite number of integrals, but we only have to integrate one term and then add them all up. At this point in the problem, x is the only variable, not n. So I just perform this integration like I would normally do. And then from here, looking at my integrand, this is a constant. Raise the exponent 1, and then put that coefficient down below. And then with this quantity here, I would evaluate it from 0 to 0.5. Now when I evaluate it at the endpoints, the endpoint of 0 is going to give me 0, and when I replace x with 0.5, it's the same as if I replace x with 1/2, meaning I'm going to have this value to the 4n plus 3 on the bottom. So the answer to the question is this. This is the value of my definite integral, but as is, it's not very useful because it's an infinite sum. So if I said, let's just consider what the first few terms look like. If I replace n equals 0, n equal 1, n equal 2, n equal 3, let's just go that far. Well, then if I simplify this, this is 1 over 24. This is 1 over 5,376. 1 over 2,703,360. The next term, 1 over 2,477,260,800. Now that's just the sum of the first four terms, but you notice that the denominators are getting astronomically large very fast. If I do a simple calculation of this, I would come up with this is 0.0041481,024. Well, that's not the final answer. The final answer is an infinite decimal. But when you check, believe it or not, if I stopped right now, I actually have an answer that is accurate to 14 decimal places, because the next term will not affect it until the 15th place, which means I came up with a reasonable estimation using just the first four terms of the power series.